Greetings everyone. Today we will discuss about the work done by torque.
Work done by torque. Let us consider rigid body which is rotated about an axis of rotation x dash. Let us consider a point P where we apply the force in order to produce the rotational effect. Let this point P is at a distance r from the axis of rotation. Due to this application of force, a rotational effect will be produced in this rigid body, which is shown by the angular displacement delta theta. Say this angular displacement produce up to point Q, which is shown by a arc PQ. The work done in the rotational motion of the body or the work done by the torque is delta W is equal to force multiplied by distance along the arc PQ. But we know delta theta is the angle which is equal to arc divided by radius. Here arc is PQ and radius, this is the distance, that is r. Therefore, RPQ is equal to delta theta multiplied by r. Hence, work done delta W is equal to force multiplied by delta theta r. Now rearrange the expression delta W, we can write Fr delta theta, and we know F force multiplied by perpendicular distance is the torque delta theta. Now the total work done by torque is W total work done delta d theta. That means you have to integrate this expression, that is theta 1 to theta 2. This is the total work done. Now rearrange the expression delta W, we can write Fr delta theta, and we know F force multiplied by perpendicular distance is the torque delta theta. Now power delivered by torque. As we know, work done is torque delta theta. Divide the above expression by delta T, that is delta W divided by delta T is equal to tau delta theta divided by delta t. We know rate of work done is power, that is equal to tau displacement with respect to time, that is angular velocity. So this is the relation between the power and the torque.
Angular component of torque.
Angular component of torque. Let us consider a plane xy in which a particle P is rotating about origin O having position vector r. Suppose a force is applied on this particle, that is F, which is making an angle theta with the position vector. Now draw a perpendicular, say ON, on the line of action of force. Draw ON perpendicular to NP. Now in triangle OPN, you can see if this angle is theta, this is also theta. This ON divided by OP is equal to sine of theta. Let's say this is a perpendicular distance, it is denoted by D. So D by OPR, that is equal to sine of theta, and D is R sine of theta. Now the torque, we know that is the force multiplied by perpendicular distance. That is, torque is equal to force, perpendicular distance is d. So we can write force F R sine of theta. Now see, this force is making an angle theta with the disposition vector. So this force can be resolved into the rectangular components, that is along x-axis, that is the radial component Fr, and along the y-axis the angular component F theta. First, force can be resolved into, first is the radial component, that is Fr. So Fr can be written as F cos of theta, because this is the horizontal component of the force. Second is the angular component. Angular component is denoted by F theta, that is F theta is equal to F sine of theta. Clearly, torque is Fr sine of theta. We can write F sine of theta multiplied by R. Here, F sine theta is the angular component, that is F of theta multiplied by R. That is, torque is the product of the angular component of the force and its distance from the axis of rotation. Hence, torque due to the force is only due to its angular component. The radial component of the force does not contribute to the torque.
That's all. Thank you.